Okay, now let's talk about how to make a test. The idea is similar to what we were doing with average values, right? So we have the proportion for the population, and we know that the sample proportion are distributed normally. So if that's the formula that brings them together, so we have plus minus and then z value, and then we have the sigma for the standard error for the sample proportions. So it means the following. If, for example, we know the sample proportion and we know a probability for getting the population proportion, then we can calculate a z value for the given probability, and then we can calculate pi. Okay. But if we know pi, and that's what usually we know in the tests, if we know pi, then we can calculate z and calculate the probability to get a proportion as we have, or even more extreme for the given null hypothesis, if indeed null hypothesis is correct, right? So these are possible null hypotheses. We either know pi exactly, or we know, for example, the upper limit for pi, or we know the bottom limit for pi. And then we do it, this is similar to what we have done in the average values. We just calculate z, which will tell us how extreme the difference between the population proportion and the sample proportion is. So it will tell us how far the population proportion is from the sample proportion in standard errors. And then we can calculate a p-value, a probability to get this particular z-value even more extreme if null hypothesis is correct. Okay. So that's it. Now let's look at some examples how to calculate the p-value using the CDF function in R. You remember that CDF function for normal distribution, it's p-norm, and then by default it's standardized. So if you want to calculate the p-value for both tails, well, the easiest we can do is to find the proportion for define the p-value for the negative z and then double it, and that's what this code does actually. And then for left tail it's even easier. You just apply CDF for your given z value, and then for the right tail you just subtract the left part from 1. Okay, so that's how to calculate the p-values. And now some examples. So we are working with the same sample as we had before, 50 engineers, and then let's test. Can we say that half of engineers know R? Okay, let's start with this one. Well, first of all, we need to calculate sigma and the standard error in this case, because we know pi, and this, let me call it pi 0, right? So we know that pi is equal to 0.5. And so that's our null hypothesis. Let me call it pi 0. Okay, that's our null hypothesis. Then we can calculate the sigma, the standard error for the population proportion, as following. So it's 0.5 times 1 minus 0.5, it's also 0.5, right? Divided to 50, and then it's a square root of this one, okay? Which gives us 0.5 over square root of 50, which is approximately 0.7. So this is our standard error for the sample proportions. Now we can calculate z value. So in this case, I will do it here. So z is our proportion for our sample at 0.4 minus proportion for our null hypothesis at 0.5, and then divided to 0.07. Oh, I forgot, this is 0.07, not 0.7. 0.07. Okay. And again, if we round it to 2 decimals, it will be approximately minus 1.43. And then if you want to calculate a p-value for this null hypothesis, that p-pi equal to 0.5, it's simply you take this negative minus 1.43. It's already negative, so you can just calculate it as a double of CDF function for minus 1.43. Okay, which gives us approximately again 0.15, approximately 0.15. Okay, so 15% chance to get a sample like we have, or even more extreme. It means that the proportion for the sample will be either below 0.5 or above 0.5. That's what will be extreme in this case. 15% chance to get a sample with proportion as we have, or even more extreme if null hypothesis is true. So that's a chance. So we cannot reject null hypothesis in this case. Okay. Then so this is true. Then can we say that at least half of engineers do not know R? So in this case, again, the pi 0 is 0.5, And then we know that sigma depends only on proportion of our population and on a sample size, so the sigma will be the same in this case. Sigma, the standard error will be the same, 0.07. Okay. Now we can calculate the z-value. In this case, the proportion of engineers who don't know R for our sample is 0.6. So we take 0.6 minus 0.5 and then divide it to 0.07, which is 0.1 divided to 0.07. And then we will have the same value as we had in the previous test, but with the sign plus, so 1.43. Okay. Then the p-value, we can calculate a p-value. In this case, because we have at least, it means that we need to use a left tail, right? So to calculate the p-value, because all negative z-values will be extreme in this case, right? So we just calculate the p-norm using p-norm function. So the p-value in this case will be 0.92. So this is pretty high value. So if indeed our null hypothesis that at least half of engineers don't know R, it seems to be correct. It seems to be, we cannot reject this null hypothesis, right? And then the last one, can we say that at least half of engineers have high salary? And again, in this case, our null hypothesis is the same. The sample size is the same, so it means that the standard error will be the same, right? Because it depends only on the proportion for null hypothesis and the sample size, so it will be 0.07. Now we can calculate the z-value. We have 28% in our sample, engineers with a high salary, so it will be 0.28 minus 0.5, that's our null hypothesis, divided to 0.07, okay, which gives us minus 0.22 divided to 0.07, which gives us approximately minus 3.14. Then you can see this value is pretty extreme for this null hypothesis, at least half, right? So it's because it's negative, right? And it's minus 3. We know that for normal distribution, z-value minus 3 is pretty extreme in this case. So if you calculate a p-value using, again, a CDF for just a CDF function because it's a left tail, so the p-value for this null hypothesis pi 0 is at least 0.5 in this case. Will be 0.3008. So we reject this hypothesis because it's very unlikely that our sample came from a population where at least half of engineers have high salary. And then similarly, you can make a test for two populations. So if you want to compare proportions of two populations, and then again you have this possible null hypothesis, either the proportions are the same, or one proportion is larger or equal, or one proportion is smaller or equal. Okay. And then of course this is the error. This should be p1 and pi1 and pi2 here. And then the idea is the same. We need to take a difference between the population proportions and then see how extreme this difference is for the null hypothesis being true. Okay. So in our case, we have the same rules as for the one sample, but now these rules should be applied for both samples. So it means that the sample size should be large enough, like this. It should be like this. Yes, and then you calculate the z-value as a difference between the population proportions divided to standard error. In this case, you have to calculate the Pullett standard error, right? And that's how to calculate it. You see, I use this p with a small dash on top of it. Then this q with a small dash is just a short for 1 minus p, like this. Okay. And then that's how to calculate the p dash, and it's just a weighted average of the two proportions. Okay. So and then you calculate z-value and use the same rules as we learned before, using CDF function to get p-value for either for equality or using one of the tails.